Hello and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I want to start out with a huge thanks to everyone who joined in on our My AI discussion over the last few weeks. We received some outstanding entries to the contest, and now it's your turn to check them out and vote for a winner. Do this by visiting our contest page at twimlai.com/myai. Voting remains open through Sunday, March 14th at 11:59 p.m. Eastern Time. A quick bit about the next Twiml online meetup. The meetup will be on Tuesday, March 13th, and Sean Devlin will be doing an in-depth review of reinforcement learning and presenting the Google DeepMind paper, Playing Atari with Deep Reinforcement Learning. Head on over to twimlai.com/meetup to learn more or register. For today's show, the final episode in our Black in AI series, I'm speaking with Zenna Tavares, a PhD student in both the Department of Brain and Cognitive Sciences and the Computer Science and Artificial Intelligence Lab at MIT. I spent some time with Zenna after his talk at the Strange Loop conference, titled Running Programs in Reverse for Deeper AI. Zenna shares some great insight into his work on program inversion, an area which lies at the intersection of Bayesian modeling, deep learning, and computational logic. We set the stage with a discussion of inverse graphics and the similarity between graphic inversion and vision inversion. We then discussed the application of these techniques to intelligent systems, including the idea of parametric inversion. Last but not least, Zenna details how these techniques might be implemented and discusses his work on ReverseFlow, a library to execute TensorFlow programs backwards, and Sigma.jl, a probabilistic programming environment implemented in the dynamic programming language Julia. This talk packs a punch, and I'm glad to share it with you. Let's get to it. Hey everyone, I am here at the Strange Loop conference, and I have the pleasure of being joined by Zenna Tavares. Zenna is a PhD student at MIT, and he spoke this morning here at the conference on running programs in reverse for deeper AI.
Yeah.
And I'm really interested in hearing more about what that's all about. So welcome. Welcome, Zenna.
I'm happy to be here.
Great to have you on. So why don't we start by having you tell us a little bit about your background, how you got interested in AI, what you're up to at MIT, all that stuff.
Yeah, so I'm from London. I studied electronic engineering for my undergrad, and I think I first got into research, or I became interested in research when I studied abroad in Japan. And so I went to Japan, and I worked in this lab. The PI for that lab, the advisor for that lab, this famous Japanese guy, you might have seen him. He builds these really lifelike robots.
Okay.
So he builds them of people in the lab. So there's one of him, and there's one of some of the lab students.
Oh, wow.
And so that was my first kind of touch of research, and I thought, this is a cool environment. And also I thought studying the brain is a cool thing. And so I finished my undergrad. I did a master's degree, which is in basically neuroscience.
Okay.
And so then after that, I thought, okay, let me come to the States, and I came to MIT, and I joined MIT in the BCS, which is the Brain and Cognitive Sciences department. So it's a mixture of neuroscience and cognitive science, which is basically psychology.
Okay.
And from there, I kind of transitioned more into the computer science side. And so now I sit in CSAL, the Computer Science AI Lab, where I work on basically using ideas from computer science and programming languages to study things about how the mind works.
Okay. Wow. Sounds like you've been a bunch of interesting places, for sure. So I read the abstract for your talk, Running Programs in Reverse.
Yeah.
And it sounds like that's a thing, like program inversion. I hadn't heard about that before. Why don't you tell us a little bit about program inversion and where's the intersection between that and AI?
Sure. So maybe the best way to describe it is how I came to the problem.
Okay.
And so there's a professor at MIT called Josh Tenenbaum. And when I joined MIT, he was talking about this idea.
Josh Tenenbaum, the networking guy? Or operating systems?
No, I don't think so. He's more of a psychologist, a scientist.
Yeah, I think there's another Josh Tenenbaum that wrote a book, and I forget which book that we use in my engineering program, either networking or operating systems or something.
Yeah, I think it's the same. It could be the same guy.
Anyway, so Josh Tenenbaum
at MIT in the BCS.
At MIT, okay.
And he told me about this idea of inverse graphics. And the way he describes it is basically like this. So you can think of rendering, this process, which we use in animation, films like Toy Story, to go from a 3D representation of the world to 2D images or a video that you go and see when you go to the movies.
Okay.
And you can think of vision, as in seeing, as the inverse of that process, in the sense that I get into my eyes 2-dimensional images, and somehow from that I infer the 3-dimensional structure of the world.
Okay.
I infer the geometry, I can figure out where the lights are, I can figure out where I am in relation to the world. And so there's this like inverse relationship between rendering or graphics and vision.
Okay.
And so it's not, I don't think it's his idea, it's an old idea in computer vision, but nobody's really taken it literally. Right? And so some other people in Josh's lab, like Tejas and Ilka, they've worked on similar projects. And the idea I had was, okay, what if we literally took this idea? Like, what if we took a rendering algorithm similar to the kind they use in, computer graphics, and tried to run that algorithm backwards from the output, from the image, literally backwards to the 3D structure.
Oh wow! Okay.
So that was the kind of the motivation, or like how I came to this project. And then after we started, there's many issues that arise, but we realized that it's actually a kind of a general framework that we can use to think about many different kinds of problems.
Okay. And it sounds like, at least in the graphics case, it works generally?
I mean, it works in the research sense, right? It works.
It produces something.
Yeah, So we have a working prototype for a particular kind of graphics. So we can take in 2D images from a fairly primitive voxel renderer. So the input are images and the output are 3D voxel shapes. So we can't do super complicated geometric structures.
Right.
But we can do kind of cool, interesting shapes, and we're doing it in a way which I don't think anybody has done before. And so we hope that we can scale up to these, to real kind of realistic scenes, but that's going to require a lot more work.
Okay. And so what you were talking about here was applying that to AI.
So I started with this example of inverse rendering or inverse graphics.
Right.
But the way I opened my talk was talking about this idea of mental simulation. So mental simulation is it's an old idea in psychology, and the basic idea is that the way that you can reason about the world, like the way that I can pick up objects or know that something's stable or unstable, is that I have a kind of simulator in my head, right? And so I look at the world, I construct a model of the world inside my head, and then I can run that simulation and figure out what's going to happen. Right? So I can figure out, this object's not stable because in my simulation it falls over.
Right.
And so one of the ways that we're trying to basically extend this idea of inverse graphics to more general problems is say, well, can we do inverse physical simulation? Right? So for example, you could say things like, oh, what I want to do is fold some clothes, right? Or I want to, pick up some object in some dynamic environment. And so one way to frame that problem is to say, well, I have some end state that I'm trying to get to. Let me run a kind of a physical simulation backwards and say, okay, what are the inputs that have to go into that system for me to reach the desired end state?
Okay.
And so that's the way that we're trying to solve the problem. I mean, many people approach this problem in various different ways. I would say that the main distinguishing point about our approach is that we really try to take this idea literally. We take real physical simulators and we're trying to run them backwards. The tools that we've developed, they're quite general, so they can apply to many different problems. So if you can reformulate your problem in terms of a kind of program inversion, then hopefully we can have a stab at trying to solve it.
And so do I need to reformulate my problem in terms of program inversion, or is that something that your tools will do or help me do?
That's something you need to do, but it's not like
and are you speaking of me reformulating my problem like at the level of a problem statement, or like I've got the
Yeah.
Not my program.
Yeah. So at the problem statement, that's what I'm talking about.
Okay.
So like, if you can formulate your problem like in your head or like mathematically as a form of program inversion, and what I would argue is that actually many problems can be formulated in terms of program inversion, right? Because programs are very general things, right?
Can you give us some examples of ones that will help us wrap our heads around the concept?
Sure. So for example, and I'm not saying that we can solve this kind of problem yet, right? But so for example, if you had a big kind of quantum simulator, right, which takes as input some molecules and as output, it says, okay, how efficient would this molecule be as in a solar panel, for example.
Okay.
Right? So this is like a forward simulator. It does all kind of quantum simulations, and it says, okay, the efficiency of this molecule, is 90% or whatever, right? So you can think of the inverse of that process as going from the efficiency that you want back to the molecule. So now you have a kind of discovery of chemicals, right?
Got it.
Or optimization, right? So optimization comes up in all kinds of fields. And so you have some loss function which takes in something and says, okay, how good is that thing?
Right.
If you can invert an optimization, if you can invert a loss function, you can do optimization. You can say, okay, here is the cost that I'm trying to achieve.
Right.
What is the input that, realizes that cost?
Right. It strikes me from hearing the examples that you gave that the challenge is that in the forward direction, the output space is like much more constrained. It's a number, right? Whereas in the reverse direction, the output space is massive, if not infinite.
Yeah, exactly. So when I first came to this, this idea, I remember I was sitting in one of Josh Tenenbaum's lab meetings. I was thinking, okay, why don't we just try and run this program backwards, right? And then obviously the first thing you get into is that often these functions or these programs are not invertible, right?
Right.
Which means that there are many outputs which map to the same, many inputs which map to the same output. And so in the inverse direction, you have a choice, right? Which way should you go backwards, right? If I've got many x's which map to y, and I'm going backwards from y to x, like what should I choose? Like, how do I do that?
Right.
And so the theory that I came up with, we now call parametric inversion.
Okay.
And it basically says if you're trying to invert a non-invertible function, so there's multiple inputs which map to the same output, we can parameterize that choice.
Okay.
So we construct this new thing, we call it a parametric inverse. So we'll take in some value y, but also a parameter theta, and give you back one of the x's which map to y. So just to give you a very simple example, the absolute value function is not invertible, right? So because if I take the absolute value of 5, I get 5.
Or minus.
Yeah, if I take absolute value of -5, I also get 5.
Right.
But I can construct this thing called a parametric inverse, and it will take in some value, let's call it y, 5 in this case, and the parameter, let's say it's either 1 or -1, and it will just return this parameter theta times y.
Right.
So the point is that the output, depending on your choice of theta, will be either 5 or -5. Right? Obviously, that's a kind of a trivial example, but the intuition or the idea that we had was, you can define these simple inverses for all of our simple functions like absolute value, addition, multiplication, sine, and so on. And it turns out with a little bit of work, actually you can define inverses for much more complicated functions or much more complicated programs.
And is the idea then with the example that you gave around finding a molecule that achieves X level of efficiency in a solar panel that you would be able to constrain by some set of molecules or, for example, that would be your parameter?
So in this case, so suppose you give me some program, this forward simulation, right? And I can construct this parametric inverse. So you'll have many parameters, and as you vary over the parameters, you'll get out different molecules with the desired efficiency.
Right.
And so if you have some further constraints, I don't know, maybe you want a small molecule, or maybe you want a molecule that you can synthesize.
Right.
Then you can add these constraints you can impose those constraints on the parameter space, right? And so a parametric inverse basically gives you the choice. You choose a parameter value, and it'll give you back a different input which maps to the same output.
And so you mentioned that you have your current research is, or you mentioned in your abstract, I should say, your current research is applying this specifically to TensorFlow programs and inverting the computational graphs for deep neural nets.
So we built a lot of machinery around TensorFlow programs.
Okay.
it's not so much that we're focused on inverting neural networks, although that's something that we've been considering. It's just that TensorFlow programs have a nice kind of representation which is amenable to our algorithms, right? And so TensorFlow,
the graph structure in particular?
Exactly, right.
Okay.
So the graph structure, yeah. So people often use it for, neural networks, but really it's a general kind of programming language, like an embedded programming language. And so we have a tool, it's on GitHub in some, kind of slightly broken state, but you can check it out. But one thing I would say is that more recently we've been moving over to using the Julia programming language.
Okay.
And so we've kind of been building our own version of TensorFlow in Julia. It's still, so we still can compile down to TensorFlow if you want to use TensorFlow.
Okay.
TensorFlow has all these great things for optimization and so on that we want to, I don't want to re-implement. So we can still compile down to TensorFlow and Python. But we moved to Julia because because of the type system, it allows us to do a lot more things more efficiently with a lot less code. So that's the direction we're going, and I would also recommend other people check out Julia if they get the chance.
So can you give me some examples of the application of this to AI systems or deep learning systems?
Yeah. So the ones I've spoken about in vision. Basically, if we're trying to build robots that act in the real world, they're going to have to manipulate objects in the real world, right? So, for example, you can pick up a cup, right? This cup on the table, and it's a little bit elastic. It has a particular shape. It has some, resistance. All these things about the physical world allow you to freely interact with the physical world, right? And so you have some physical intuition. And I would argue that in order to build robots that aren't so rigid in how they interact with the world, we're going to have to kind of embed that physical knowledge into their brains as well.
Okay.
And one way to do that is to allow them to have a simulator in their mind. But many of the things that they'll use the simulation for are kind of inverse simulation. So they'll see, for example, they may see the cup on the floor and they can figure out, it fell over at some point in time. Or to go to the lower perceptual things, like how does a robot learn to see? How does a robot see in the world? Well, it's got to take in images, in its camera eyes, and somehow figure out the geometric structure of the world. So it knows that the door, is so far away. It can disambiguate between the colors of the lights versus the color of the material. So I think many of the core, I don't have a concrete thing that we're trying to build, but I think many of the core problems in AI, this kind of technology is relevant to. It's still a research project. I'm in research, so this is the kind of thing that we do.
And so you were careful to kind of distinguish between TensorFlow as a general programming framework and its common use in deep learning, but does the work that you've done and the results that you've seen with ReverseFlow apply to deep neural nets that are constructed in TensorFlow? And are there any practical examples that you can cite of taking a real TensorFlow program and doing this program inversion to it and having it produce something?
Yeah, so there was a lot of, there's a lot of work with adversarial examples recently. And but before, there was work basically saying, okay, if I've trained some neural network, I want to find out, what inputs would cause a kind of weird misclassification. Right? So people have worked on this for a little while. And so in some sense, we can invert neural networks in the sense that, even a complicated neural network eventually just boils down to some sequence of primitive operations.
Sure.
Basically multiplications, sums, and some non-linearity. And even that non-linearity also boils down to even simpler things. So because our inversion algorithm is defined in terms of these primitive operations, in principle, we can invert, a neural network with the current framework. But in practice, it's not the best way to do it. And so one of the things actually we've been working on is how can we kind of take a better approach to inverting neural networks. And so to the second part of your question, why might you want to do that? For me, I think the most interesting application is, again, inverting models of the world. So I've worked on inverse graphics. And to do that, I write down a normal rendering algorithm. I happen to write it in TensorFlow, but I could have written it in Python or C or so on. But I think humans, we learn algorithms. We learn algorithms, from experience. And so it would be nice if we could take a learned algorithm, so something like a neural network, and also invert that. So I can do inverse graphics, but the algorithm that I'm inverting is a more realistic version of reality.
Is the implication there that you're inverting not I guess the picture that I had in my head of this was that you're inverting I guess an architecture absence of like having been trained. But it sounds like what you're saying is you're the learning is coming in through the training, and so we're inverting this trained neural network model.
It's not something that we're doing right now. So right now
it's all conceptual.
This is conceptual. I mean, maybe like a better example would be in like physics and dynamics. So we can build pretty impressive physical simulators that work well for rigid bodies and some elastic bodies, but they're not so good at things like hair, for example, and they're not so good at simulating things like cloth. And yet humans can still, manipulate cloth. We still have a good intuition about how that works. And so I think a learning approach could supplement that. So we can maybe have some part of that model which is, handwritten, and some part of that model is learned from experience. And there are people who are working on this right now.
It's interesting. So one of the examples that comes to mind for me is there are some folks at Berkeley in their intelligent robotics lab that are applying reinforcement learning to teaching a robot how to tie a knot, right, in a rope. And so, the rope, the robot is basically trying to mess around with the rope and learn the rope dynamics.
Right.
And it sounds like, the approach that you're describing would be, I don't know, how would the approach you're describing fit in that? It's like once you learn this model for kind of basic rope dynamics, you can invert it to, like what is the conceptual thing that you're inverting it to?
So like the way you have to formulate it in this way, you'd say, okay, I have a model of, rope dynamics, right? And you can think about this as probably a temporal model, right? So the time is the variable, and I have some desired state, like I want, after some amount of time, t whatever,
right,
I want the rope to be in a knotted state, right?
Right.
And so the inputs to that system are my actions. And obviously the system also acts in the absence of me doing anything, right? And so it's the inversion in the sense that I have to figure out what are the actions that I need to input into the system for me to tie the knot.
Right.
And so this is...
As opposed to these actions produce this model. Right.
And so, in some ways, people have an intuition. It's like, if I want to do something, like, what do I have to do for that to be true?
Yeah.
And so that's how you would formulate the problem in this way. But the rope dynamics, as I've been saying, this is something I think you could learn, right? We don't, maybe people do have, good models for rope dynamics. I'm not sure.
I think it's still work in progress.
Right. Okay. So, yeah.
Interesting. So what else did you cover in the talk?
So the first, I talked a bit about Julia. I would say that the first, 10 minutes was, actually I talked a lot about psychology experiments.
Okay. From what perspective?
So there's an experiment from the 1970s. So these are all about this idea of mental simulation.
Okay.
And it's kind of hard to describe without diagrams, but the basic idea is called mental rotation. The basic idea is that you can see different shapes, and they're either the same shape, but rotated from different angles, or they're different shapes, right?
Okay.
Different shapes entirely, right?
Okay.
And so people did these studies where they said, okay, look at many of these shapes and say whether you think they're the same or whether you think they're different. And what they found is a very tight linear correlation with the angle of rotation and the amount of time it took people to respond.
Okay.
Like lending some support to the idea that the way people answer this question is that they look at the shapes and they do a kind of mental rotation and they say, oh, I can rotate shape A into shape B, and like if they're more, if
the more rotated, the longer the
Yeah.
simulation takes.
Yeah, and so like a kind of a whole subfield of psychological research came out of that idea. And so some part of my talk was saying, okay, this is, obviously there's a lot of cool work there, and obviously they've done a lot of studies. Can we take that idea and make it computational? Can we build computational models of it? And can we build an AI that can do something similar? And if we were to do that, what kind of technologies would we need? What kind of algorithms would we need? So like personally, I'm motivated by like cool, interesting, small studies like this, which pinpoint something interesting about how the mind works. And then you realize that despite all the kind of cool stuff that's happening in AI at the moment, deep learning, there are all these really simple things that we really haven't even got the right way to think about, right? And so those are the things that interest me most.
Right. Cool. And then you mentioned Julia. You mentioned the type safe aspect of it. Is Julia something that comes up a lot in the context of AI? Does it lend itself to that type of work specifically? I haven't heard it come up in that context much.
Yeah. So I mean the main frameworks for AI are definitely in Python, right? And I guess there's Torch, which is Lua, right? But I would say Julia is building momentum. So Julia, I mean, it came out of MIT, and the people who developed it, were kind of data scientists. Maybe not machine learning people as such, but people who use MATLAB or C. I think I was watching a talk, and one of the main developers, he said he had this huge stack of C, R, MATLAB, and Python, right? And it's like, why is this so complicated? And so that was kind of the birth of this language. So the main points are that, one, it's very fast. It's dynamic. It's also compiled. And it has a kind of interesting type system, like a multi-method dispatch type system.
What does that mean?
So like in an object-oriented language like Python, for example, or C++, right? You have some object, like, I don't know, you have like cat, and you do cat dot, make a sound, right?
Cat dot meow or whatever.
Cat dot meow. In Julia, the methods, this is what people call a single dispatch, right? But in Julia, the methods are not part of the object. They live in like a separate space. And so you would do meow, which takes in an object of type cat, and it would meow that cat. And so obviously you can do more things. You can have meow taking an object of type cat and some other object, like dog, and the cat meows at the dog. So it sounds like a simple thing, but it turns out that if you build your language on that principle, lots of nice, elegant features fall out.
Is this related to the concept of mixins?
It's definitely not used in machine learning so much, but I would say there's a few packages like flux.jl. There's also a TensorFlow binding, tensorflow.jl. And so I think it's gaining momentum, and I think because it's built on like a nice set of core principles, I think actually it has the opportunity to strive as a machine learning language in the future. That's why I put my money.
Nice. And does it presumably it has some kind of native or provided by a package strong notion of matrices and arrays and all that kind of stuff.
So all of that stuff is built in, right? And it's really well designed as well. They put a lot of thought into how to take what was good about MATLAB, discard what was bad, and so you have multi-dimensional arrays, and you have all the kind of things that you would expect from like a numerical programming language. And it's fast. Also, there's like a GPU library now, so you can call native CUDA if you want. So there's a lot of stuff.
Okay, cool. Did we hit on everything that you covered in your talk?
I think so, pretty much, yeah.
Awesome. Well, thanks so much for taking a few minutes to chat with us.
All right, thanks a lot.
Appreciate it.
Thanks.
All right, everyone, that's our show for today. For more information on Zenna or any of the topics covered in this episode, head on over to twimlai.com/talk/114. Definitely remember to vote for your favorite My AI video at twimlai.com/myai. And of course, thanks so much for listening, and catch you next time.